Thank you. All right. Good morning. Yeah, I have the privilege of updating you guys about what's new in CCP-EM. So the first talk I'm splitting it with Joel. So I'll give the general updates with CCP-EM, and Joel will talk about the heterogeneity challenge, and you'll hear more about it later. Okay. So that works. So I'll start with the workshops and events that we run and we contribute to, and what has happened last year and what are upcoming. And also in terms of the software suite we have, what are the updates to do with that? Okay, in terms of workshops, we run several workshops every year. So this is a list of workshops which we have run and we have a significant contribution to. So this is since the last symposium. So we had the last one 2 weeks back in India. So end of March, early April this year. And we also run several road shows. So what it means is that if you're interested in using our software suite, and if you are not sure whether it fits to what you want to do and so on, we're happy to come to you and give you a demonstration, talk to you, take you through it, and also to help get things installed in your institute to get things up and running. And we have a set of workshops lined up from now until end of this year. So the next one is actually next week in Czechia. It's a model building workshop, and we have quite a few of them lined up for this year. So you will find information about the workshops and events in the CCP-EM mailing list. I'm sure most of you are members of this already. And if you have questions about events or roadshows, you can also contact us directly at ccpm@sdfc.ac.uk, and we are happy to help with things. Okay, so for those wondering what is Doppio and who have not used it before, so Doppio is our software suite version 2. So we had a version 1 software before this, and this is a complete rewrite of things. So it's built from scratch, and this Doppio is a web-friendly interface we have, and it basically is made of 2 main layers, the GUI layer, which sits in the front end, and you can launch it in a web browser or a standalone application. And the GUI layer is called Doppio, but we tend to refer to the whole thing as Doppio when we talk to people about it. But what sits underneath is the pipeliner layer. So that's the important component. So it manages the job and workflows, how the jobs are linked to each other, and how the project workflows are structured and so on. So we have the way it is designed, we've driven inspiration from how things are structured in Relion, and we also work closely with Shaw's and his group in this development. So Doppio itself has an SDFC license. It's free for academic use. Pipeliner is fully open source. And all the jobs that you would like to run, what we call as plugins to Pipeliner. And these are essentially a few lines of Python code for each plugin. And this fits into the pipeline, and the pipeliner manages the jobs. Okay. So since the last symposium, the release with last symposium was version 1.3, and now we are at version 1.6. It's a beta version because there are some features that needs more extensive testing before we release a stable version. But if you are using this version and if you have feedback, if you find any issues, it'll be very useful for us to go back and fix things before we make a stable release. You can download Doppio from our website in the download link, and there's a user guide which will guide you through the installation and getting you started with it. We have a set of online tutorials, and there's been some recent improvements with it. So you can, if you go to these links, you can find the standard tutorials and also those associated with different data sets from various workshops that we run. Because Doppio works with a variety of external tools, what we call as plugins, when you install Doppio, you don't get all of them together with Doppio, so you often have to install the additional tools. We already have a system in place for installing some of them. So if you go to the install additional packages link from the Doppio project tab, you will have access to installation of some of these tools. And we are trying to improve this installation process with access to more of the plugin tools. Okay, so what's new in 1.6 version? And so here's a list of some of the highlights in version 1.6 beta. To start with, we have the job continuation support, and you can also overwrite existing jobs now. For the particle picking job, so if you have, we have more interactivity in place for this. So if you have a set of picked particle coordinates, you've used some automated picking tools for it, and you want to curate it, delete some of the picks or add new ones, you can do this interactively now on the visualization tool we have on a web browser. And you can save these picks as a new selection of particles and so on. We have support for working on multiple Doppio projects simultaneously. So this was not the case before. And you can launch different Doppio instances and work with different projects in parallel now. The support for scripts for custom visualization with CAHRA accent code. So what it means is that you can launch these tools with specific visualization commands from Doppio. And you can then do things like color maps models with certain attributes and so on. There's been several improvements to different visualization aspects. So specifically the kind of validation plots, the B-factor distribution, and so on. So you have more information in there. There's more indicators on how for better interpretation of these model map FSCs. And these are part of the validation and refinement jobs. I'll take you through the other highlights in more detail in the next few slides. So one of the new things or new tools we have support in version 1.6 is the local template matching tool. So essentially, if you have to search for, if you have a template high resolution structure and you want to search for the position and orientation of this template in a 3D tomogram, you can use this tool. And it's developed by Rangana, who's part of our group, and he is also in the audience somewhere. So if you're interested, you can ask him for more details of things. So there's a variety of things that come with this. So there's a set of pre-processing tasks. So you can prepare templates, create masks. So the masks are used mainly for the calculation of cross-correlation. You have the template matching job by itself. You can also do some post-processing. So depending on the number of hits you get, you can filter it based on a z-score thresholding and so on. You can also visualize these, the results in Napari. Okay, so you have these interfaces to use in version 1.6, and these are the list of jobs associated with it. and you have different results visualization. You also get a Rely-on style star file with a set of particle coordinates and orientations. Okay, so another tool to highlight is what we call a DPI score. So it's a deep learning based tool for evaluating protein-protein interaction. So if you have a complex made of multiple protein-protein interfaces, you can run the score and get scores for each of these interfaces. So here's an example from EMDB. It's an actin complex built at low resolution. And you have DPI score highlighting some of these interfaces have low scores. So there's potential probably to improve this. And if you do a bit of re-refinement and automated workflows in Doppio, you can improve this interface, and the DPI score also improves. There's a few improvements with respect to visualization of results. So one of the things is particle angular distribution. So in the refined 3D jobs, for example, you now get display of the 3D histograms of angles. So you might be familiar with this already. So the support for this build files in refined 3D in the Molstar viewer we have, and you can also open it along with the maps and also hide maps and so on. There's also the 2D kind of a projection display of the angular distribution, which you are, I'm sure, are already familiar with. So, so that bit was developed by Yola, who's already in the audience. So if you're interested, you can chat with her later. I mentioned about CCP-EM Pipeliner. So that's the kind of manager for the project workflow. And because we keep track of different jobs and the workflow and how the jobs are linked to each other, and how is the data flow between jobs in a project, we can essentially track the data and metadata that goes along with this workflow. So what it means is, if you have a job, let's say it's a job which resulted in your final reconstruction, you can trace back from that job to all its parents. So you can trace a critical path through the workflow and gather all the metadata associated with that workflow. So essentially, you can keep track of what all parameters and metadata has gone into that path. And this is a record for future use. So if somebody else wants to run this workflow and they have access to these metadata to essentially reproduce the same thing. We also record the literature references for different tools. So it's good to cite whatever tools you use in the publication. Okay, so as one of the, I think it's an important project we have. So it's all driven by Matt Ayadansa in the group. He's also here in the audience. So we're working with Diamond and the data banks, so namely EMDB, PDBE, and Empire, in streamlining the deposition process. So what it means is, so if we can standardize the metadata schema that is required for deposition, we can essentially record this in the processing workflow. We can gather the metadata that comes associated with the microscope data collection, and also the sample data, for example. So if we prepare a CIF format file with all the metadata that is required, and also add it with the metadata that we trace in the processing stages. So we have everything then we need for deposition. So you don't have to manually fill in all the fields in the long deposition form, which you usually otherwise do. Okay, so we have, Matt has added support for this in Doppio, and we have jobs dedicated for this. So we have the deposition job and the Empire deposition job. So it already gathers all the metadata required, and also you can add in additional metadata externally as well. So you prepare one ZIP file or a JSON file which is ready for deposition to the data banks. And this bit is nearly ready, and you'll hear more about this from Kyle late after in his talk. But I think this will be ready in the next few months. So it's something coming soon. One other project we've involved with ABIC and Diamond is looking at the data storage. So it's one of the things that is quite important for a facility like ABIC and for other facilities and data centers is how we manage the data storage of what we collect and produce and process. Essentially, we generate loads of data every year. So it's roughly 10 petabytes. So this is numbers from 2023. I'm sure the numbers are much higher now. And in a typical workflow from Diamond, you have the raw movies is quite significant, the space, the storage requirement for that. And the process data is roughly, say, 55% of the workflow. So this is for an SPA processing pipeline. The question then was, can we think a bit about how and what we store? So can we store the data better? Can we compress the raw movies, for example, in a better format? So the motion corrected micrographs, so it accounts for nearly 47% of the whole data in the workflow. So that's quite significant. And then the obvious question is, do we really need to store that in the archive? And can we generate this on demand quickly? So we looked at these two questions, and we benchmarked the raw movies data sets from ABIC against different compression methods. So here are some results from some of the data sets that we looked at. So typically we get an integer 8 type data, which is the electron counting data we get, and they are typically TIFF files which are pre-compressed. So we looked at whether if we apply different compression methods, can we get better compression? So we identified methods like BLOS-Z standard, which is also used in other fields like volume EM. You will hear about this later as well. And they compress better than the LZW compression we typically use. And if it's an integer 16 type, they are less sparse and compress a bit worse. But you can improve this, it seems. And the compression speed is also much faster than LZW compression. So you can gain, you have some stepwise gains here. It's around 5% or more, but overall it's like 0.5 petabytes in a year. And also if we get rid of motion corrected micrographs from the storage, you save that 47%. So we modified Rely-On to be able to calculate motion corrected micrographs on demand. So if you have pre-calculated shift parameters from a previous run, you can use it and generate this on demand. And this, motion corrected micrographs calculation is added as a job continuation in Doppio. Okay, so as part of this, we also developed a software toolkit, which is we call this EM Encode, and it supports different format conversion. So it handles TIFF and MRC files, and you can convert it to different compression formats. We are also looking at exploring other possibilities, whether we can add support for these formats in processing workflow, and also looking at lossy compression and so on. So we have Willow and Mariam, who are the main drivers of this project here in the audience. So you can ask them questions if you're interested. We have a couple of kind of upcoming things that I want to highlight. One is Doppio Live. So it's on-the-fly live processing support in Doppio. So this is coming very soon. And George is kind of spearheading this thing along with Stephen and Dan from ABIC and Gillum from Diamond as well. So essentially what you can now do with Doppio is to do live data processing. So this links with data collection, and as and when you get new data, you can start processing this data. And this should be deployable to other facilities or other labs, and it needs configuration of the local resources, GPUs, and so on, but it should be able to set this up for live processing for you. So on the front end, we have Doppio now, along with certain components from Diamond, so what we call as Peto. So it's we have the dashboard from Peto, which keeps tracks of the progress of things and summarizes how the processing progresses. Underneath, we have a manager layer. So it's similar to how the Doppio itself is structured, but you have a manager that keeps track of incoming data and what jobs need to be run and what jobs are scheduled and so on. So that is taken care of by this layer. And you have the tasks as part of the workflow as well. Another new feature about that's upcoming as well is about latent space visualization. So this is a Cryo Dragon job, which is supported in Doppio. So the latent space embedding of the conformational space that Cryo Dragon produces. And what we can do now is to cluster them with different clustering approaches and look at specific clusters of interest, and also do selection of set of points. So this might be the conformation you are interested in, and create a new selection with this subset, and for downstream processing. So, and this will be supported as well. And lastly, I would like to flash this flyer about CAST 17. So CAST 17 is in preparation. I'm sure most of you know about CAST. So it's the competition about assessing different model building tools. So it's been mostly AlphaFold, which has been dominating this competition in the last few years. And this year, they would like to do something slightly challenging, in the sense that if you have new and interesting structures, which cannot be solved easily by, say, AlphaFold 3, so those are the kind of targets that they are looking for. So they want to explore the weaknesses of the automated AI-based model building tools and how we can address these weaknesses and so on. So if you're interested, you can contact the CAST organizers about this. So I'll stop with that, and I'll hand over to Joel to talk to you about the heterogeneity challenge.
Good morning, everyone. So yeah, I'm Joel. So today I'll talk to you about the CAHRA Challenge. So this is a CASP-inspired community initiative, which we at CCP-EM are running in collaboration with our colleagues at the Flatiron Institute and at Princeton University. So whilst we know that you can reconstruct high-resolution visualizations of biological macromolecules utilizing cryo-EM, actually faithfully reconstructing the full range of the structural heterogeneity present in cryo-EM datasets does remain a significant challenge. So datasets may include continuous motions, discrete states, compositional variations, or you might want to estimate population densities. So in general, in the last 15 years or so, dozens of algorithms designed to extract or interpret the heterogeneity present in CAHRA datasets have been published. We collectively refer to these as heterogeneous reconstruction algorithms. In general, they will take in a picked particle stack as an input. They may also utilize pose or consensus reconstruction information, and they often seek to represent the heterogeneity present in CRO-EM datasets in a low-dimensional representation or latent space. Often they can also make volumetric predictions of conformational or compositional states. So in order to actually assess how successful a given heterogeneous reconstruction algorithm is on recovering the heterogeneity present in a dataset, we can utilize benchmark datasets and metrics. So for the CAHRA challenge, we've curated 3 datasets. The first of these addresses compositional heterogeneity. So in this dataset, we have an unknown mixture of different complexes. And this is geared towards the development of algorithms or workflows which may enable automated visual proteomics in future. The second dataset is geared towards conformational heterogeneity. So here we've sampled conformations via a molecular dynamics simulation and then used these to create a set of synthetic micrographs. In this task, we asked participants to reconstruct a predicted ensemble of atomic models, which best represents the heterogeneity present in the dataset. And the third challenge dataset addresses the problem of pose entanglement. So in this dataset, we have a non-uniform pose distribution, and it contains 2 discrete states of a macromolecule. And we set participants the challenge of estimating the relative populations of these 2 discrete states. So I'll go into a little bit more detail about what's in these challenge datasets and how we're assessing them in the next few slides. So for the compositional heterogeneity dataset, we provide a particle stack of 1.6 million particles. As I say, this is a mystery mix of different complexes. We ask participants to reconstruct as many of these different complexes as possible. And we're assessing entries to this dataset based on how many of the complexes you managed to reconstruct, the resolutions of these reconstructions, and the accuracy of your particle assignments. For the compositional heterogeneity dataset, we provide you with a particle stack of 1.7 million particles, along with the poses from a consensus reconstruction and the FASTA sequence of this molecule. So the task that we're setting here is we want participants to determine an ensemble of between 10 and 100 different atomic models, which optimally represents the heterogeneity present in this dataset. So we will assess the predicted ensemble against the ground truth ensemble by how accurate it is, how similar the local flexibility of the 2 ensembles are, and on what proportion of the entire conformational change predicted ensembles are able to recover. For the post-entanglement dataset, we provide you with a particle stack of 30,000 particles and template maps for the 2 discrete states that are present. So here we're challenging participants to determine the relative populations of the 2 discrete states and also to make per particle state assignments and to determine the poses for each of the particles. And in this data set, we're assessing all of these based on an accuracy-wise basis. So the final deadline for challenge entries is June the 1st this year. We have a follow-up challenge review workshop, which will be held at the Rutherford Appleton Laboratory in September. Registration for this will open in the coming weeks. Please be aware that the winner of each challenge will have access to a travel and accommodation bursary to attend this. And there's also, courtesy of our collaborators in Princeton, there will be $10,000 worth of monetary prizes for top entries. We already have 11 preliminary entries across the different challenge datasets, and we'll be releasing the rankings for these in the coming days. So if you'd like more information about the CAHRA Challenge, please do come and talk to me, but you can also find all of the information you will need on our challenge website. So you can reach it via this URL or using this QR code. So on the website, you can find links to sign up for the CAHRA Challenge mailing list for announcements, a link to our GitHub discussions page for any questions or discussion about the challenge or challenge datasets. It's also where we host our leaderboards. There's links for you to download the challenge datasets on there and full instructions for making a submission to any of the different challenge datasets. Please do be aware that we welcome entries from anybody. So whether you're new to using heterogeneous reconstruction algorithms, whether you use them in your scientific studies, or whether you're a methods developer, if you can, please do get involved in the CAHRA Challenge. So I'd like to thank our collaborators on the challenge and everyone who's contributed to it here. But finally, on behalf of the CCP-EM group, I would like to thank our funders, in particular the MRC, who provide our core funding. And I'd also like to thank all of our collaborators. So thank you very much.